This time we'll be introducing the concepts of the resonant frequency and the Q factor, which are parameters which allow us to characterize the frequency response and, as we'll see later on, the step response of second order systems without having to solve the quadratic equation and find out the exact location of the poles. First, let's have a look at the mathematical definition of these parameters and see how we can calculate them from the frequency response. Well, we've seen that the frequency response of many systems, in fact all second order systems, can be written in this form. Where A and B are parameters which depend on the circuit. In the example circuit that we saw before, we got a frequency response which was j omega squared LC plus j omega times RC plus 1. But you can write this in terms of a standard form in the resonant frequency, omega naught squared. Well, omega naught is the resonant frequency, omega naught squared is the square of the resonant frequency, and the Q factor, like this. And it's quite easy to work out the resonant frequency and the Q factor when you've got the frequency response in a form like this. All you have to do is equate the coefficients of j omega and j omega squared. So, for example, in this case here, comparing the coefficients of j omega squared would tell us that 1 over omega naught squared is LC, and therefore that omega naught is 1 over the square root of LC. And we could get the Q factor by equating the coefficients of j omega, this term and this term, and getting that 1 over Q omega naught is equal to RC, and therefore that Q must be equal to 1 over RC omega naught. We've already worked out that omega naught is 1 over the square root of LC, and therefore Q must be the square root of LC over RC, which is usually written in the slightly simpler form 1 over R times the square root of L over C. And that's got our Q factor and our resonant frequency in terms of the parameters of our circuit without having to solve any quadratic equations. Now, we know how to sketch the Bode approximation of the frequency response if we know the break frequencies of the poles, but it's also possible to sketch an approximation just by knowing the resonant frequency and the Q factor. But to understand how to do that, you have to know the properties of the resonant frequency and the Q factor. So that's what we'll be looking at next. First, we'll look at the resonant frequency. Well, as we've seen, we can express the denominator of the frequency response of a second order system either in the standard form that we've seen before, in terms of the product of two factorized terms, or in this new form, in terms of the resonant frequency and the Q factor. Well, they must be equal, so if I multiply out this standard form and get 1 plus j omega minus p naught plus 1 over minus p1 plus j omega all squared over p naught p1, I can compare the coefficients of j omega squared between these two standard forms and deduce that the resonant frequency, omega naught squared, must be equal to p naught p1, because this term must be equal to this term. And therefore, the resonant frequency is the geometric mean of the poles, the square root of the product of the poles. Interestingly, it's also the frequency where the impedance of the capacitor and the impedance of the inductor in our series RLC circuit cancel out. Since in the circuit that we were looking at, where you had a resistor, a capacitor, and an inductor in series, the denominator came out to be j omega squared LC plus j omega RC plus 1. And therefore omega naught is 1 over the square root of LC. And the frequency where the impedance of the capacitor and the inductor cancel out is where j omega L plus 1 over j omega C is going to be equal to 0. And that occurs when j omega L times j omega C is minus 1, or in other words, when omega squared LC is 1. And that's just the resonant frequency that we've calculated previously by comparing this term here to this term here. But there's another property of the resonant frequency which makes it particularly useful when estimating the frequency response of circuits. And that is that the resonant frequency is the intersection between the high frequency approximation and the low frequency approximation to the frequency response. To see this, consider a general Bode approximation to the frequency response of this second order system, one with no zeros in it. At very low frequencies, h of 0 will go all the way down to dc. J omega would be 0, this term would be 0, this term would be 0. You would just end up with 1 over 1 or 1. Express that in dBs and you'd get 0 dBs. So we start off at 0 there. At very high frequencies, we would have that this term here in the denominator would be so large that it would completely overwhelm the other two terms in the denominator. So we can neglect this term and this term at high frequencies and just end up with 1 over j omega squared over omega naught squared, which is omega naught squared over j omega squared. If we're just interested in the magnitude of this to get the amplitude response, then we can equate this to just omega naught squared over omega squared. We don't have to worry about the j's. If you plot this on a Bode approximation of the gain in dBs against the log of frequency, well, that's going to give you a straight line, this straight line here, the high frequency approximation. If I convert this expression to decibels, I would get the gain in dBs, again at high frequencies only, this is a high frequency approximation, would be 20 times log to the base 10 of this, which is 20 times log to the base 10 of omega naught squared minus 20 times log to the base 10 of omega squared. Now, the log of omega squared is twice the log of omega. So I could write this as 40 log 10 omega naught minus 40 log 10 of omega. And that is the equation of a straight line. This is my y-axis, my y value, the gain in dBs. This is my x value, the log of the frequency. This is a constant, and this is a gradient. So if I plot this high frequency approximation on this Bode diagram, I'm going to get a gradient here of minus 40 dBs per decade. And if I extend this asymptote and extend the low frequency asymptote, those two are going to cross where the value given by this approximation is equal to 0. And that would occur when log 10 of omega naught is equal to log 10 of omega. In other words, omega is equal to omega naught, the resonant frequency. So those two asymptotes are going to join at the resonant frequency. And that's what makes it a useful parameter to know if you're trying to sketch the frequency response. What about the Q factor? Well, we can express the Q factor in terms of the poles by using a similar technique, multiplying out this form of the standard expression and getting 1 plus j omega 1 over minus p0 plus 1 over minus p1 plus j omega squared over p0 p1, equating the coefficients of j omega and finding that 1 over q omega naught is equal to minus 1 over p0 minus 1 over p1, which is minus p0 plus p1 over p0 p1. Turn everything upside down. Q omega naught equals p0 p1 over minus p0 plus p1. Now p0 times p1, the product of the two poles, that's just the resonant frequency squared. I can then cancel out one resonant frequency from both sides and end up with Q equals the resonant frequency divided by minus the sum of the two poles. Or as I've written it on the slide, resonant frequency divided by the modulus of the sum of the two poles. And this is an interesting parameter to know when you're plotting the amplitude response, because the Q factor tells you the gain at the resonant frequency. The frequency response of this circuit, 1 plus j omega over omega naught times Q plus j omega squared over omega naught squared. If we're actually at the resonant frequency, then the omega naught squareds here cancel out. The omega naughts here cancel out. And we're just left with 1 over 1 plus j over q plus j squared. Well, j squared is minus 1, so that cancels out with that, and that just leaves us with q over j. If we're only interested in the magnitude of the frequency response to get the amplitude response, that's the magnitude of q over j, that's just equal to q. So the Q factor is the amplitude gain at the resonant frequency. So if you want to sketch the amplitude response, and you know the Q factor and the resonant frequency, you could just extend this low frequency asymptote to there. The resonant frequency there, we could go down by 40 dBs per decade, and we would know that at high frequencies we must be on that line. At low frequencies we must be on this line, and knowing the Q factor we would know the gain at the resonant frequency. If we go up at 20 dBs per decade from that value there until we get to this asymptote, and go down at 20 dBs per decade until we hit this asymptote, then we've got our Bode approximation of the amplitude response without having to solve any quadratic equations. The only slight problem with this is that it is perfectly possible to choose components which gives you a Q factor of more than 1. That suggests that in dBs, the magnitude of the gain at the resonant frequency would be actually up here somewhere. So how do we sketch the Bode approximation in this case? Answer, it's tricky. We'll look at some techniques for estimating the amplitude response in this case later on. For now, I just wanted to show you some examples. Here are some frequency responses of circuits, all normalized so that their resonant frequency is 1, but with different Q factors. You'll see that with very low Q factors, below 1, this technique here works absolutely fine. Once you get to high Q factors, where you have some gain at the resonant frequency, this technique is not going to give you a good estimate of the amplitude response. This is known as a resonant peak in the frequency response, and we'll look at how this happens and why this happens in the next videos.